Hello, welcome to the first class of serious statistics and econometrics. Maybe this week, well, like 2 or 3 classes, we are going to review the basic probability theory and statistics concepts. So you need to know to follow the whole semester, and you better know to start your research in the future and will help if you understand those concepts. Obviously, it will help you better understand uh, like many applied models. So let me start with probability theory. So the very beginning in the in the probability theory is to think about how the randomness is generated. An important concept here is the experiment. So you have to understand what is an experiment. It's simple, it's not new. This is exactly the experiment you know, but we are going to make a structure to understand the randomness. So in statistics, by the way, there are many different approaches, different philosophies to understand randomness in statistics, like Bayesian, frequentist, and there are different philosophies. None is wrong. Like so, all are correct and all have their strength and their weakness. But I'm going to just stick to this concept because it's general enough and uh, it's useful enough, and you don't need to understand the underlying debates of the philosophical background. So I'm not going to touch that, but you need to understand at least one philosophy, and I'm going to use the frequentist approach, which is the uh, uh, majority in statistics and econometrics. Like as I said, Bayesian is a strong alternative, but I'm not going to consider that here in this review. So let's think about experiment. In the frequentist approach, the experiment is considered this way. There is a, say, black box, and from the black box, you pull out a ball. Inside the box, there are a lot of balls, and on the ball, there are, let's say, numbers, or you randomly choose one out of the box, right? So then that's how the randomness is generated. It's like a lottery ball, drawing a lottery ball, and most of the random objects can be explained by this simple framework. And we put notation. Capital omega. Capital omega is the sample space, which is the set of all balls in the box. So in the black box, there are a lot of balls, possibly infinite number of balls could be inside the box, and you put your hands there and choose one random ball, and the collection of the balls in the box is omega. Like for example, this is just everything you wanna know, like everything you choose from the set from which you choose the outcome. For example, all people on Earth. If you want to study, like say, average income, then your set of interest is like everyone. Or if you think about randomness in stock market, then the box is all possible stock market scenarios for tomorrow. By the way, yeah, I'm recording this video on Monday, and have you heard about GameStop stock market episodes? It's really funny, and if you have time, have a look at that. You may get super rich if you are super lucky. I It dropped. So for the first 1 hour of today market, it dropped 30%. Stock market, one single stock dropped 30%. I'm not sure what's happening since then. I'm looking at the stock anyhow. So you don't know what happens in the stock. So in the box, there are all the possible scenarios you can imagine, and you are choosing one of them. And then a ball in the box is denoted by lowercase omega. Omega is just one element in the box, and when you choose it, when it realizes, and it is your outcome. For example, you choose one person, or you choose one stock scenario which is observed, which realizes and observed by the researcher, and then you can understand the random variable as a function that maps the outcome, the drawn object, to a number, to a vector of numbers. So it is simply, it's defined as a numerical description of the outcome or outcome from an experiment. So you may just think it as a function. I think it's better to understand it this way. So for example, when you choose a random person, I choose a random person, then the function, there is a function x, and it maps, it extracts, it describes, x describes the person in many numbers. Like for example, the age or sex or race or height, weight. There can be more. So even if you draw once, you may have many variables. So still it is one experiment. That's an important point. You did just one experiment and you draw one randomness, but you have in this example 5 random variables. So that's a subtle difference, but the structure is quite straightforward. Or if you observe a stock market scenario, then you can draw a lot of things like say return or like opening price, closing price, right? Or how many stocks are traded. So there are many quantities, there are many variables you can describe how the stock market is going on a day. So that's an example. So here is why did I explain this? So in many cases, many students are confused with the unit. So for example, suppose that you have individual income, and you observe that like you have many individuals and you know their income and where they live, like their zip code. And on the other hand, you have data of the median housing price of each zip code. Then you would like to connect them. Of course, it's not a big problem, but when you compare them, you have to think about the difference in their units. So individual data are based on individuals, but median wage is based on zip code. So when you choose one median housing price, you are choosing one zip code, and it's not an individual. So in that sense, these two data sets do not match directly. Of course, you can manipulate the data to match to each other, but many students just don't understand why it does not work, but they encounter some things. And also another thing I would like to emphasize here is you have to think about what is the sample space. You have to define that. For example, are you like say when I study the average income, then what is your average based on? So for example, I may be interested in average income in New York State, or average income in the United States, or you may be interested in average income of those like say who are younger than 30 years old, or average income more than 60 years old, for example. So when you define your research question, you have to define the limit of your interest. So if you're interested in New York State, like data from outside New York State is useless, or you need to make additional assumption. Like as I said here, there was a huge minimum wage increase in Washington State, but if you are interested in New York State, then actually Washington State data are useless. But of course, you may make some more assumptions such that Washington State is similar to New York State. So but it is not statistics. So connecting, making some assumptions is not from statistics, but within the statistics, you have to define the sample space. So for example, what I said here is you analyze Washington State minimum wage increase effects, and you would like to apply that to New York State. Then that is not the job of statisticians. Whether New York State will behave similarly to Washington State, is the judgment from economic theory. So that is different, but rigorously you have to think about the sample space, the limit of your interest, to define it well. And here is another example. If you want to study unemployment rate, your one data may be based on state by quarter. So New York State, 2020 fourth quarter. Or on another data set, you may have data on individual level, whether each individual is employed or not. In this case, observational unit is a person at a certain point. So these two data sets have different units because their random experiment, choosing one random object, is different. So in this case, you have to think about how to match those two data sets, right? Otherwise, your analysis will be totally misleading. Many students don't understand why their data are not correct, or like why strange results happen. But in many cases, the reason is because of this. Okay, so that's how we define randomness and how we think about experiment and sample space. I will continue this part in the next video. I will resume in the next video. Thank you for watching.